Продължаваме с нашата програма. Със следващото участие професор Хайнц, Миклас и екип. Дана Hürner, Manfred, Schreiner, Wilfried, Federica, Cappa. Contemporary methods of manuscript analysis, description, and localization. Please.
Thank you, dear. Благодаря ви, Антонита и Лисенска. Аз няма да говоря. Ние сме направили едно видео, понеже сме една група и искаме всички да бъдат участници на този симпозиум. И спикърът ще бъде наш най-млад член. Това е Симон Бренер. Сега той ще се включи с едно видео и ние след това можем да дискутираме на живо, но в момента аз ще се изключа и се извинявам, че няма да бъда виден.
Заповядайте.
Сега чакаме да нашия колега да си... Ето.
I will try to share the screen. Let me know if everything works.
Yes.
Dear colleagues, for long, manuscript analysis and description was the domain of philologists and historians. During the last 20 years, however, computer vision scientists have laid the basis for a computer-aided way of investigation on the screen, especially for manuscripts which are either badly preserved or happen to be rescripted, so-called palimpsests. In various projects running over the past 15 years, our SIMA group of philologists and scientists has also introduced two other disciplines and methods that do not concern the text of the manuscript, but its material, makeup, and handling over the centuries. This is the chemical analysis by spectroscopy and the microbiological analysis of the DNA and the metagenomes of parchment manuscripts. But we have also improved the philological approach. Since time is short today, we will just mention three of the approaches: the philological, the computer vision, and the chemical one. First, philological methods. Two of the major aims of manuscript description and analysis is the dating and localization of undated codices. Since the end of the 18th century, in the case of their scribes, this has been mainly done by paleographical means. For manuscripts written on paper, watermarks gradually gained ground, and especially in Paleoslavic studies, phonetic, phonological, and graphemic, usually called orthographical, criteria have widely been used for the times of Vatroslav Jagic and August Leskian onwards. Presently, we are expecting additional possibilities from analytical examinations. Indeed, at least in the case of the so-called Sinaitic Missal, these expectations have already been fulfilled by the results of the microbiological analysis, which confirmed our philological localization with the Sinai. Other such examples will follow when the material basis has become large enough for close comparisons. Even so, the most important tools for dating and localizing manuscripts remains to be the philological ones. That means we have to refine these methods to perfection. Thus, Dana Hürner and Heinz Miklas developed tables for the comparison of Glagolitic and Cyrillic scribes that during the following work proved to be extremely helpful. Meanwhile, we have applied them to all Glagolitic manuscripts and fragments of the Old Church Slavonic period. Contrary to older comparative tables, they are not based on one single letter specimen per scribe, or even per manuscript as in many instances, but on all extant character variants which can be found on the relevant folia of one scribe. This, of course, assumes the correct delimitation of the scribe parts in the respective manuscript. The example shown here is quite simple and concerns the oldest Slavonic manuscript, the so-called Kiev folia. In the future, we want to add a computer software which automizes the comparison of different hands. The other method Heinz Miklas and Dana Hürner developed is a graphemic tool for dating and localizing Old Church Slavonic Glagolitic scribes. It has also been successfully tested in the analysis of well-known as well as newly found manuscripts. Here, 20 classes with altogether 50 graphemic features are sorted out and then calculated on the basis of empirical, chronological, and redactional values. In other words, The graphemic features and their assigned values are counted and result in arithmetic figures. This may sound difficult, but is very easy and reliable. The picture you see derives from the analysis of a small liturgical fragment found in the Sinai only in 2017. The next part of this talk will be about multispectral imaging. This is an imaging method useful for restoring degraded writings, such as in this example. So, how does it work? In conventional color images, you have 3 channels, one for red, green and blue. In a multispectral image, on the other hand, you have multiple such channels, each for a specific wavelength. And normally multispectral imaging does not work only in the visible range, but extends the spectral range to the infrared and the ultraviolet. So we both increase the spectral range and the spectral resolution in comparison to normal images. These figures show the spectra that are recorded by an RGB camera versus the spectra that are recorded by a multispectral image. And this way it's possible to distinguish different areas on a manuscript surface, such as points that contain ink residues from former writings or just plain background areas. Our multispectral image acquisition system is based on multispectral LED panels that are able to produce 11 narrow wavebands, such that the response of the material to each of these wavebands can be recorded individually. With the help of a filter wheel, we are able to distinguish between UV fluorescence and UV reflectography. A high-resolution achromatic camera is then used to record the reflected light. Here you see the system in operation at the Ivan Vazov library in Plovdiv. On the left, you see the system setup inside the darkening tent, because during acquisition there must be no external light. In the middle you see how operation is working when the lights are turned on. And on the right side you see acquisition software, where you can define a list of images that you would like to make, and then the software automates the whole process. After acquisition, the multispectral images usually need some post-processing in order to acquire useful results. First step is usually the registration. It means in all the multispectral layers, the same surface points should be visible at the same pixel positions. This is not always the case, because for example when you use different imaging devices with different resolutions, those images are not perfectly aligned. Also, when you change optical filters between shots, they can introduce little image shifts. Then there is the problem of chromatic aberration, that is that light of different wavelength has different refractional angles and thus take slightly different paths in the camera's optical system and hit the sensor in different places. Also, it's possible that the manuscript itself is moving during the imaging process, because when you take it out of a controlled climatic environment, then the pages can start to curl up, for example. And also it's possible that you accidentally move some parts of the acquisition system during the work. After registration is done, statistical methods can be applied in order to combine the information contained in all of the multispectral layers. This can be decomposition algorithms like principal or independent component analysis, clustering methods, or classification methods, where you can define different classes of pixels such as background, black ink or undertext, and then learn to assign to each pixel the class that it belongs to. Here we show an example from the Plovdiv National Library. On the left you see the RGB color image, and on the right you see the UV fluorescence image. In this fluorescence image you can already see that there is an undertext present, but it's not so easy to see and to discern from the main writing. After applying an independent component analysis, you end up with these components, for example. The left one shows the main text, the middle one shows the undertext very brightly, and the right one shows a little bit of both. When you then put them in the color channels of an RGB image and combine them, you end up with a so-called false color or pseudo-color image, where you can then clearly see the undertext in a different color than the main text, and this way it's very easy to read it. Here we see another example from the Plovdiv library. So this is the Gospel fragment of Kyustendil, and again on the left you have the visible light image, in the middle you have the UV fluorescence image, and on the right image you see the results of multispectral imaging with some post-processing applied. Here is another example from a Greek manuscript, which was very heavily degraded. This is another Greek manuscript, and in this case we applied the linear discriminant analysis, which is one of these classification approaches that we were talking about earlier. Now we show how analytical methods can be used to determine the materials used in the manufacturing of a manuscript. It has to be mentioned that for the material analysis of manuscripts, we are applying only so-called non-destructive and non-invasive techniques, which means that no original material has to be gained from an object, and that the instruments had to be transported into the collection. In this talk, we demonstrate the use of our methods on measurements conducted in the Ivan Vazov library of Plovdiv. The investigations were carried out already in 2017 by Bernadette Frühmann and Federica Cappa, using X-ray fluorescence analysis or XRF and Fourier transform infrared spectroscopy in reflection mode or RFTIR. Our analysis had two major goals. On one hand, exact information on the parchment and the writing materials, such as inks, paints and binders, was to be obtained, and on the other, we wanted to collect data for a comparative study of parchment degradation and its relationship to artificially aged modern parchment. These figures depict the XRF device Elio by the company XG Lab in Milano, Italy, which was designed and built for non-destructive analysis of art objects. As is known, by XRF, only elements can be detected. Applied in air, only those with an atomic number higher than sulfur. From the elements detected, in many cases conclusions can be drawn concerning the pigments which are present in various colors. However, to get a full picture, it needs a complementary analysis, and FTIR, here in the reflection mode, serves for detecting organic as well as inorganic substances and compositions, both in the parchment and in pigments and writing materials. Furthermore, it was successfully used to detect materials used for conservation and restoration treatments, such as gelatin or starch, as well as contaminations with wax. As an example, the next slide shows the FTIR spectra obtained from the parchments in two manuscripts in the library in Plovdiv. On the left side, a comparison of the spectra from the two manuscripts shows remarkable differences in the yellow-marked spectral regions. A comparison of the spectra to reference database spectra further showed that calcium soaps and silicates were detected on the parchment in the manuscript inventory number 7, matching in the blue and gray marked regions on the graph in the middle, whereas in the manuscript number 18, only chalk was detected on the surface. Please note the blue marks on the graph on the right side. This shows that different manufacturing techniques were used to make the parchments. Calcium can appear when the parchment was whitened with lime or calcium carbonate. Silicates can derive from the polishing of the surface. In the following, we exemplify further results obtained with a combination of RFTIR and XRF analysis obtained for the inks and pigments used in the Q-Standil fragment, inventory number 7. The XRF results of the investigations of the black and brown inks in the text showed the presence of iron in higher amounts compared to the parchment, together with potassium and sometimes small amounts of calcium. This can be related to iron gall ink. Moreover, in one spot of folio 3 recto, small amounts of chlorine were found, as well as some arsenic on folio 8 verso, which is also common for iron gall ink. Inks of the text passages on the margins mostly contain potassium and iron, and can therefore be iron gall ink as well. In one point of interest on folio 4 recto, only potassium was detected, which argues for the use of a carbon black ink in this case. The red ink in the text as well as the marginal notes showed mercury with sulfur, due to the red pigment vermilion. The red pigment in the initial is similar to the red ink used for the text. XRF investigations identified mercury, which indicates vermilion. Lead was detected by XRF in a wide area of the initial, and the RFTIR result showed that lead white was mixed with gypsum. Furthermore, the results suggest the use of an organic pigment, such as indigo, mixed with lead white and gypsum on the bright blue and white orpiment in the greenish-blue parts. In the yellow areas, sulfur, potassium, and high amounts of arsenic were detected by XRF, which indicates the use of orpiment or realgar as a yellow pigment. In the last part of our talk, we would like to address hyperspectral imaging, which can be viewed as a hybrid between multispectral imaging and spectroscopy. Like multispectral imaging, we acquire data for a two-dimensional surface. However, instead of tens of spectral layers, hundreds of layers are required, such that for each pixel a full spectral curve is obtained. So we have created our own easy-to-use hyperspectral image viewer, which we will now use to demonstrate the use of hyperspectral images. So here I can click on the left side on each pixel of the image, and on the right side I will get the corresponding spectrum. So for example, if I select the blue here, I will get a raise of the curve around 700 nanometers, which is typical for the pigment indigo. On the other hand, if I select this blue over here, I will get a very different spectrum. Similarly, if I select a red part, for example here on the eye, or this one, we get a typical spectrum for the pigment minium. If I switch here to the similarity tab, I can visualize which other pixels in the image are similar to the one that is currently selected. And as you can see, here in the horns, in the eyes, around this part here and on the column here on the left, we find the same pigment. Then again, we can select some black ink over here, and we see that we have a strong rise in reflectivity in the infrared range, which means that this is not a carbon-based ink, but perhaps iron gall ink. In contrast here, this calibration target is made with a carbon-based black material, and you can see that it is highly absorbent also in the infrared range. Another thing you can do is that you can scroll through the different wavelengths. So here in this corner you see the wavelength that we are currently looking at. And as you see, if we increase the wavelength, here for example, the red parts start to become reflective, because we are here at around 600 nanometers, where you can see a steep rise in the curve here. And if we go further up, then the blue starts to get reflective. These parts, which start to reflect at 700 nanometers. And what is still black in this range are, for example, the green parts here on the left. For comparison, this is the RGB image again. Another thing that you can see is that there are no underdrawings here, at least not with any carbon-based ink, because here in the infrared range you see that everything is just reflective and there are no underdrawings visible. Of course, you can also export every selected spectrum in a standard format that can then, for example, be compared to spectral databases.
Thank you.
Dear colleagues, for long, many...
Thank you very much.
Не знам, ако имаме още време, можем и да дискутираме, ако...
Имаме време, да. Заповядайте.
Само, че аз ще включа английския сега, иначе моите колеги няма да разберат.
Заповядайте.
If you want to talk a little bit with us and discuss things which we have heard on this morning, I think this would be a good occasion. So please be free to tell us more about what you've seen, or to ask questions, or whatever you want.
Whether do you analyze zographensis, codex zographensis, and the parts which are inscribed by Cyrillic letters under the Glagolitic?
I'm sorry, I'm not sure whether I understood you. In the Glagolitic manuscript, whether there was what?
Cyrillic letters under the text of Glagolitic.
No. Yes, there was. Indeed, there is one, but I'm not quite sure whether it's Greek or whether it's Cyrillic.
Oh.
And that's the small booklet of medical folia, 3 double folia, which were found in another book, the Psalter of Demetrius. And
yes, I know.
You know that. You have heard about it.
But I speak about Codex Zographensis.
No, not in the Zographensis, because in the Zographensis there is a Glagolitic underlayer, which has been partly published, but the rest, there's still a large rest, which should be detected and read and published. But unfortunately, our colleagues from the library did not give us the permission so far. I mean,
but
tried
language characteristics of that text, which is beyond glagolitic, is younger than language characteristics of Codex Zographensis.
Of course, it's a little bit
it's
younger,
very interesting.
It might be a little bit younger, but not much, because the handwriting is so similar that I would not exclude even from the same school somebody wrote these, you know.
Thank you.
Audios.
Thank you.
Mm-hmm.
So I finished.
From our group, we have an IT specialist. This was Simon Brenner who spoke, and we have Manfred Schreiner, who is our chemist, and who is responsible for the last part of our video. So if you want to put questions on a chemist or an IT specialist, this is the occasion to do it.
Yeah, I have a short question.
Please.
Thank you very much for very, very interesting presentation. I wonder if you can, the additional organic stuff on the manuscripts, like wax or, I don't know, tears, or do you take this in consideration?
Wax is actually a very, very interesting topic, which has been tackled recently, especially in England and by Russian colleagues in St. Petersburg, but we have not tried to do anything on wax so far. But we have done microbiological investigations so far on 4 manuscripts and found extremely interesting results. One of them being that a plant was used for a blue pigment in the so-called Sinaitic missal. And this plant was partly affected by a virus. Don't ask me which, I forgot it now. But if we had time enough, we would have shown it to you. Anyway, in this result showed that we have to do with a pigment which was used in Egypt. Even in ancient Egypt, the colors of the eyes were made of this pigment. So my philological localization of the manuscript with the Sinai is very obvious by the microbiological investigation. So I was very, very happy, you know, because the plant was grown in Egypt from ancient times up to now, you know. That's just one of the, but there's many, many later, how shall I put it, stuff to be detected on a manuscript, of course, because you use the manuscript and everything which you touch by your hand is already microbiologically changed somehow. So you find all kinds of viruses, all kinds of bacteria and things like that, you know, from ancient times up to now. And in the future, I'm sure that many such investigations, if you compare them, may even be a basic for tracing the way of a manuscript. You know what I mean? From a certain area to another area and so on. So this is a very, very interesting topic, but we need much more material. You need thousands of manuscript investigations in order to really show something for sure.
If I may add some or complete the answer of Professor Miklas as a chemist concerning the wax can be easily detected by infrared spectroscopy, as you probably know. But nevertheless, we cannot decide whether the wax is part of the original manuscript, or if it's from the candles, or if it's from conservation restoration treatments. So in general, wax can be easily determined and detected by infrared spectroscopy, but we never know whether this comes from the original material or from the conservation restoration treatment, which was carried out during a period, several times, a period of, I don't know, 800, 900 years, as you know. Yeah.
Well, we do not want to consume your time, so I give you back to the word.
Thank you very much.